and today we explain about my assignment. So let's just go straight to it. So you can see in here that about a given code that the teacher gave to me, and it tell me about how I import about a new library, and then it show me about the way I can like visualize my code. And this is like about the dot, like the example of it, like about the knot. We write about the two knot, and then we are drawing about the edge of it, which is knot one connected to knot two, and then we make it more complicated in here. So let's go to about the section 2. We create about a binary search tree. You already know like about we got like about a binary search tree with a on the left side, which we got like about a not less than the root, and on the right side we got like about a not is greater than the root. And if we got like about a binary search tree, it got like about the disadvantage about if like about the depth of the tree is too deep. For example, on the left side, you got like about really low, whether the deep is equal to 1. But like on the left side, we got like a deep equal to 20. If when you are searching it, when you're searching that thing, if in and unlucky for you, like about your knots, you want to get it, it like about on the right, like it on the right side at the bottom. So you need to go to every like about go to everything in order to get that thing. So that exactly it's also making about the time complexity is more, like about more sophisticated, and it also like about make it like about it not like about it not easy to like maintain and update. So that's the reason why we need to use it in another way. So I'm still like about explaining about how battery surgery working. Yeah, and because like about is we have about more understanding about AVS tree, black red, like black tree, red black tree in the future. So like to show you, for first thing I'm create about the class node, and inside of it what I have in here. So what when you're getting about the nodes, you just got about the value bit. Whether it's on the right side or the left side of it, whether it's got like a parent node and a balance, we check and a balance of it. So we are building about a binary tree in here. We check like about a random not equal to 0. If land equal to 0, it lists empty. Otherwise, we write about a binary tree. And a binary tree in here is it talking about how we are doing it. We got like a middle, root left, root right, and then we're testing it. And yeah, and this is how the way we're testing it, and we are building about how we are building a bit like about this is about the code we want to like visualize the tree the teacher had given to me. So we are just like about visualizing it when we are using about a dot library into visualizing it. So you can see in here we got the about the tree in here, which like about is already balanced, but like when you are implementing about a new thing itself, it's just like not balanced like this. So yeah, it testing the tree in a different case, and then in the section 3 we are element about the searching, inserting, deleting. So yeah, let's just go straight to it. So the first thing we are searching the tree, we are checking whether about whether it's got like about the value equal to the not value is not, whether it's equal to the root is not. So if it equal to the root, we return true. Otherwise, if that thing is less than about the root, for example, just go into the left side, and then we're checking it. Otherwise, we are just going to the right side. And when you are going to the left side, you don't need to go to the right side to check it, because we are totally know that the knot we are want to find that on the left side. So that's the reason why we create about the function depth in here. And we are testing about the search tree in a different case. If we return true, because we can find about that knot in our tree. Otherwise, if not if not finding that knot in our tree, it return false. And let's go to another thing like about the function insert thing. Insert, and we are still got about the value with we checking whether the knot we got or not. So we checking whether like about we got like enter 3 or not. If it is enter 3, we return about the not values, and if it already exceeds on the not, we are just return nothing. So if that value is less than, we go to the left, and then if it's greater than, we go to the right, and we are count like about create a function of it in the to like install the shutting. And we're testing in here, so you can see in here we are got this thing, and after we are inserting like about the not with the got the value is -1.5. So it exactly we just going to the left side and we install in here. Not about the mean value knot. So the mean values knot we are the teacher in here is like it to find about in order successor when the root we want to delete have two children. So if that's thing, so the root if not we are want to delete it exactly which is the on the on the last. So it doesn't have any children. So the easy we just delete it, then that's it. If it is not, so we need to call about the delete function and we need to do a lot of things in here. So like just go straight to it. If not equal to none, we just return about a not. If the value is less than, if we did the not on the left side, we need to delete that thing, and we need like about on the right side, we need to delete that thing with the value bit. Otherwise, it's on not with like only one child or no child with each chicken it. We can like about return about a temporal knot of it. I like about we write about a temporal knot on the right side, and then we check and we like about aside about the knot we want to delete into none, and then we return about a temporal. Similar case what about on the right side. And yeah, we return about a knot, test 350 in here, and we are inserting the tree. Yep, and you can see in here we are inserting and everything. Yeah, and this is about how we deleting. Yep. So in the section 4, we are all the thing we are like about the assignment. So let's go straight to it. So the modified about biology tree, so then keep track a bit balance for the verbal question. Like I said before, like biology, like about the thing above, which is like about the like about the basics biology tree, but like it's not balanced. So we need to modify about a little bit, modify the code a little bit in order to make it AVS tree. So AVS tree, we got like about a rule bit. So everything is need to be like about the deep of the tree is need to be less than or equal to 1. If it is greater than 1, we exactly just like it will not like about it will not satisfy our condition and about the AVS tree. So yeah, let's go straight to the code. So we first thing I want to like modify the knot, and we're adding a new field to start about the hair of each knot. So you can see in here everything is the same except I'm adding about the hair bit because like I want to check in whether the hay is like whether it's balanced or not. So we checking whether the hay is like about less than or equal to 1 or not. Yep, and then we're getting about the hay, and then we update the hay. So we're getting the hay because like I want to like get in the hay of the knot. So if we not getting any knot, so it's mean like none. So we return 0. Otherwise we're getting about the we return about the knot of the hay, and we are update about the hay of every knot. Yeah, and the reason why I'm using this thing because like about we need to like update every knot because we want to check whether it's balanced or not. We not only like about taking about the hay of that knot, we also need to take the back like about the hay of every knot. So yeah, that's the reason why I'm taking a 1 equal plus max, and then we check in here on the right side and on the left side, both sides. And next thing I need to like checking whether it's balanced or not. So we are taking the knot in here. If it is not a knot, man, it is nothing. We just like about return true. Otherwise, we need to like return about like about the value of the left side minus the value of the right side. Must be like about less than or equal to 1 because I've already tell you like about if the condition of the AVS3 must be the hay is less than or equal than 1. So yeah, and then if it is not like about if it is not like about balance, we need to doing a different k in order to make it to the into the balance tree. So we are going about performing about a rotation to maintain the balance. We need to perform rotation, and the first thing we need to like getting about a knot of this thing, and then we are making it onto the left side, and then the T2 to the right side, and we are performing a rotation. We update about the hay, and then we returning a similar structure to like a rotating left, and then we're returning about y in here. Yep, and then the next thing we need to like inserting about the knots. So we are performing about a normal Barry string system, and we are checking whether it's in a knot or not. If it is not a knot, so we return about that knot. So yeah, and if the key is less than the knot value, which means the root, So if it's less than, we just going to the left side and we insert that thing, otherwise going to the right side. And we update again the hey, and then we're checking whether it's in balance or not. And if, and we also got like about inside it, we also got about a different case because like we checking it, if not unbalanced, then we got like about four cases arise. So the first thing we got like about a left case, like about if balance greater than one and the key is less than about the not left values. We started just using about rotating right, and then we also got like about similar structure but on the right side. So the right case we call it about right case, and then the left right case. So the left right case is just simply is more complicated a little bit than about the left case and the right case. Like about we instead of rotate one, we need to rotate two times. So yeah, we rotate about if the balance is greater than one and the key if the not left is greater than also. So we need to like rotating left and then we're rotating right again. So similar structure to right left case, and then we return that's not. And yeah, if we got like about the insert the knot, we also get about the deleted knot. So yeah, if we want to delete a knot, we just got like about the key value bit. If it is not a knot, so we'll return that knot. Okay. Okay. Let me just put it again. Okay. All right. So let me just run it. And yeah, we did the case when I had no children. We are checking in here, and then we check like about check if it did not have left substrate. This means like the not to be deleted had no left substrate, so the could so it could have none or just like one to the right. So and if it did not let is none, we instead of just like about store about the right substrate in the temporal variable temp. We're just storing it, and then we are delete about that knot by assigning that the knot we want to delete into none, and then we are return about the temporal tree. So we got like about a new tree, and then we already delete the knot. Yep, similar structure to the right like to the right things. Yep. And then we are deal with about not have two children. If we got two children, we that which is called about a function mean value not, and then we are uh, taking about the temporal values and then into like assign into the not the value and then not to the right and equal to delete not right and then the temporal values. So and then we check in again, we update the hey, we get a balance similar to like about it when inserting in here, and we are testing whether it's balanced or not. If the tree is balanced, if it is not, we return true. If it not is balanced, we return false. And then we return about whether the balance on the left, whether the on the left side is balanced or not, and whether on the right side is balanced or not. If two of them is balanced, we just like return true, and we just like return two of this thing, two of the like about the substrate. Yep. And yeah, we are testing this in how the way I'm testing it, like about I'm checking whether it's valid or not, and then I'm inserting about the new values, the new knot, and then I'm delete that new things in that thing. If it returns true in everything, it's fine. Otherwise, I need to check about what code. So let's go straight. Let's just run it. So you can see in here we got like three true with it. Everything is correct. My like about all the thing is correct, and then my code is true, and then I need to like visualize about my update about an update of visualization function display the each node. So I need to like visualizing it, so you can see in here we got like about the hay a bit, so and everything is fine because like about it's not like about it's still certified about the hay is little bit less than or equal to 1. So you can see in here we got like hey 1 2 3 on the left side, on the right side 1 2 3 things. Yep. So let's go to about the next question, like the next question like about right now algorithm and call to find the first common ancestor of two knot in a Barry search tree and find argument of two knot things. So yep. And so this is my code because I'm already like about using I'm already implementing everything before both. So all the thing I need to do like about create about a new function to find about the first common ancestor of two knot in the Barry search tree, and then I'm taking about the list of the three knot, and then also like about a not one, not two, in order to find it. If the root is none, we check, we just return none. And we are and then I will check like about check if the value of the current knot, which is about root value, is equal to the value of knot one or knot two, then the current knot is the nearest common ancestor. And we are checking again if the knot both knot one and knot two have value less than the value of the current knot root value, the nearest common ancestor, but on the left subtree. Recursively called about a phi common ancestor function with a left like left subtree, and similar structure to like on the right side. Yeah, and then I'm checking it. So you can see in here I'm creating about example of the how I'm putting about the tree in here, and I'm making like about right, left, left, right. So when you are seeing it, you exactly would just like about see like about what which is about the ancestor of it. So we can see like about the ancestor of 2027, which is like right, left, right, and about left, left, left is 3. And if we the first one ancestor of two of them is 20. So I don't know whether they got like about the parent or not, but like their first ancestor is 20. I don't know because like maybe they have like about a different parents, but their first common ancestor is still 20. Yep. And this is how I visualizing everything in here. So yep. So in here I need to like create about a new thing, which is I'm not creating everything new except like about I'm checking whether my structure like about my right right rotation and then left rotation is correct or not. So let's just go straight. We got like about the initial tree with the like about we got a hay a bit, everything is fine. When I'm adding a knot 30, so it go into here, and yeah, which is like about it's already rotating it. So I'm checking in here. I'm checking whether it's rotating or not. Yep. Because like about our thing, because like about the end, the question is asking me whether it's rotate or not. Yeah, and then it needs to the different tree in here, so you can see the left rotation at 20, and then when the left right rotation at 20 in here we rotate, and then the right left we also like about rotating it. So every rotation, my rotation is working. So that's how we working. So let's go to about the next question, about question 4, about a red black tree. So you can see in here when we are rotating about a red black tree, we get to like follow the different it's more sophisticated, and we need to follow about the condition of how it be working. So every button is red or black, and then the base of the tree is always black. All leaf new is black. If the knot is red, then both with children must be black. And any simple path of that knot of the child leaf contain the same number of black knots. So they can go straight in. We are great about the initialization of the red, red black knot. Red black tree has been working. In here we got like about a color, value, whether it's from like everything is same except we got like about a new thing like about a color in here. And then create about the new class with about with the name of black tree, and create about initialization with we create about the lip a bit, and also the root, which a the root of it, and which is about the sentinel new knot, and then create about the insert thing. Instead of just like about read a new knot first, and then this line, and then this line not left not right, set left and right children of the new knot to the new sentimental knot. So it is exactly just like about a knot, a new thing in here, and the new knot which within the new leaf, which is always black. It cannot be red. So that's the reason. So that's the things, and we are adding about the knot into the tree, make sure they correct and the rules of the battery search tree. So it's just similar to like the AVS tree. It's similar to the AVS tree, except like about it adding more function. It adding more function about like about it not like about care much. Is it less than like it's less accuracy like a AVS tree, because like about for example, for AVS3, when you're adding one knot, you also need to check for everything. Like about when you got like about the thing is too big, And then when you're adding just one more knot, you need to like checking again about whether it's a balance or not, which is like about it's more take a lot of time, like about a red black tree. Yeah. And this is how about inserting and then deleting the knot. Find the knot using a function, find knot in here. If it is true, we delete it using a function delete knot. And then I'm checking whether the insert knot which are following rule or not. And then making a loop until the current point is null. So I will like about go through every loop and then check all the condition. And I'm also like about update about the point of the current node in here, making the color a bit and find the node if you want to using it, and delete the node, checking the condition again. And the next thing I will show you about, because I'm writing here the list like find about it in all the successor. This means like about take larger node to replace in test instead of using a smaller node, because like some visualization you can maybe when you are deleting thing you need to like about you can like about taking on the left like about the thing like the less than the your knot, or maybe you can take the knot really greater than your knot. So yeah, and writing about it, find a minimum knot in here, red change plan, you for changing the knot U into V in a tree. Important for deleting knot in red black knot in a fixed insert. Also thing this K for about a child, K for like about child knot on the left. And in here I'm checking different case a bit. Like about you can see like about K uncle is red. If K uncle is red, we change the color of K uncle and the father to black and the color of the K father to red. And then we move K up to the place continue checking. So this is all the case with to be like about checking in order to like satisfy all the condition with black tree. So we got like about K2, K uncle is black, K child on the rise, and then similar to thing like about K uncle black and red. Fix delete, fix delete also same, we checking about the condition like about the like about different case when they're deleting it. The first case like sibling of red, sibling had two children both black, sibling have at least one red child, and then we checking it. And then we also checking like about KX on the left. So the thing about we checking things on the this thing like we checking it on the yep, we checking on the left KX on the left child node. And in here is similar things. So the thing above we checking on the left, this thing is checking on like about the right channel. So yep, this thing we're checking on the right things. Yep. And yeah, I'm great about the function left rotate, right rotate in here. The same about show you example got like about a checking condition whether it's in new or not. So and I'm visualizing it. The first thing I will insert and deleting the tree with RBL3, inserting the value bit and the value equal to this, and after insertion, let's just run it to see it. So you can see in here we got like about the RB3 after insertion, everything is fine. APL3 don't meet all the requirement. Then like about the red thing is here cannot be going with red, and like it also like using APL3 and the new leaf in here. Yep, everything is fine. When I'm delete about the knot 9, delete number 9, we exactly we just like about making taking about the knot on the greater than it into here. And then we're deleting number 4 in here because like about the 4 the lift the knot at the bottom, so it don't have any like about child or don't have any child, so it's still we just deleting it and nothing to do. And after we deleting number 2 in here, so yeah, it we also taking about the knot greater than 2 into like about the parents of it. So yeah, so that's the case. And yep, and I will show you I'm already show you about this thing. And the next thing I will show you about, because the reason why I'm like about highlighting the thing above like about instead of taking like about the thing yep, in here I'm taking about not greater than instead of less than. So let's just go straight for my example in here. So I will just think about two inserting thing is we just think about using red black tree in another website. 12 5. Okay, so 5 9 10 3 6 7 and 4. Yep. So you can see in here everything in the same amount of like about of my visualization. So and then after I'm deleting the number 9, what happening? So I'm deleting net not number 5. It taking number 7 because like it taking the not with it less than. I'm using about the thing that is greater than. So I'm taking number 10 here into this thing. So you can see in here number 4. I'm deleting it because it is like about the not at bottom had no child, so we're just deleting it without and doing nothing. Everything is done. So after delete number 2, it exactly was just taking number 1. We're taking number 3, similar to me. So that's the reason why I want to highlight about the thing, the minimum cut I want to show you. And let's just go to about the next thing, which is our working. So about the B plus 3. So consider B plus 3, and then instead the teacher just give me instead of the number, they give me about the 3 order m equal to 3, which like about the name it, and we need to like assuming the lexicographic ordering. So which means like about A equal greater than B greater than C, something like that. So instead of just like keeping like about making it like getting escape, I'm instead of just like writing it. I'm also like about make it like about like about ascending. So era is create era number 8, band number 3, band number 4. I'm still following about the lexicographic order. I'm just writing it. I'm adding about number 1. You can see in here number 1, which is no, it's just like about number 12. Where was it? Okay, we got like about 16 things. So number 16 in here, and number 16 is 3 6 9 3 6 9 is 1. So 1 is W. W says like about is it about the smaller thing. So yeah, I'm just adding here, and then I'm just like inserting here because we are using about the B plus 3. The B plus 3 is just similar to like the modification of the B tree, except it we celebrated 5 more thing more easier. And yeah, and about the value of that's not is storing at the leaf, is not storing at the not and the value of it. So that's the reason why we can find it. We can find value is more faster than about a B tree, the normal B tree. So yep, let's just go straight. So you can see in here I'm insert number A, number 3, 3A in here. So we can see in here we got like about 3 key. Why not have 2 keys? Because the maximum is 2 key. Because I'm already it's because it's telling about the number order is M3. So the maximum not in that the maximum key in that knot is 2. So if it is greater than 2, we cannot like about we need to like modifying it because like about it like about it uncertified about the AVL3. So that's the reason why for 3 4 8, because you can see that not too many key, so we need to take like about the median of it into the two up things, and then we are like about 4 going here, and then A going here, 3 going here, and then A going here. So you can see in here we still certified about the battery search tree, and then also certified about the AVL tree also. So in here, because 3 is less than, so it's going to the left side. A is greater than, so it goes to the right side. It's a thing 11 also. Too many key in here and unsustained, and we just like about splitting it. We are just putting about the median number 8 into the bottoms, and then we are connected number 4, number 8 in here, and then connect because like about the knots which are the minimums, the minimum knot in the minimum key in that knot in number 1, but like the maximum key in the knot in number 2. If it is crater, we need to like putting it above. So that's the reason we're gonna do this thing. Yeah, and then it's just in number 7 because like about we meet the standard thing, so everything is fine. It's just number 13, 15, 14. After that, it's just in everything. And yep, at the bottoms, after it's a thing, everything with its 16 values, we got this result. Where was it? Okay, so yep, we got this result, which is like about this thing. You can see in here is where you can see in the knot, it not have totally 16 like about 16 value of 16 value because like about every like about every values is stored on the lift. So the lift is just like about like about it's easier for the shutting thing. So, and yep, and let's because like about the AVS3, we are usually use B plus 3 and a B3 into like about the things that it into database because like about we are want to store about our data into this, and we're not using it to store into RAM. So that's the reason why we're using about for the B plus 3, the B and the B plus 3 in this for the database, which is really large data. We like about starting really large data. And yep, and do the above for the B3. This is about how the B3 doing the same, except like about the knot we are using is like about instead of the key with the value, the notch with the value bit. We're not starting about the value inside the lip, so that's the reason why we got in here. So we are too many not in here. We're taking about a median into the above, which is satisfy the condition. We are doing the same. You can see in here, too many key in here. Number 8 go to in here, and adding 13, adding 15. Too many key. Put 13 into here. Still too many key because we got greater than 2. So we are putting number 8 into the above. We got number 8, 14. 16, 1, 2, and then doing the same until we got like about this thing. At the end, I'm just taking about okay. Now what is number 8? So we got like about number 8 is error that lock key and everything. So we got like about the converting work into B3. So yeah, that's it all my explanation about the assignment. Thank you.